Gnanam Paramam Dheyam. Knowledge is supreme.
Okay, welcome back to this second half of this lecture on polynomials. Last half I have defined what a polynomial ring over a ring is, and I will continue with some basic properties of the polynomials which we will you keep using in this course. I will still be little briefer and faster because in principle what I am doing now is a prerequisite for this course. So, remember we have a ring R and we have constructed a new ring called polynomial ring in over R or polynomial ring in one variable over R, and actually we can repeat this process. So, we can repeat, now you can take this ring R, Rx polynomial ring, and then we can consider a polynomial ring over this ring in the second variable y, but this is same thing as a polynomial ring now in two variables over R, and this way you can construct polynomial rings in many number of variables. Okay, so note that for each polynomial f, these ai's are called the coefficients of f. A0, A1, etc., An, they are called coefficients of f, and when this An is non-zero, this n is called the degree of f. This is denoted by deg f, degree of f, and this coefficient n is called the leading coefficient of f. So, important thing to note is immediately the formulas for the degrees. So, for example, what happens when I add two polynomials, what happens to their degrees? So, I will only say check, I am not going to prove this, but check this, check that. One, if I take f and g two polynomials and then they look at the degree of f plus g, that is less equal to degree f, look at degree f, degree g, and take their maximum. Less equal to. Remember, less equal to, it is not equal, it is less equal to, because I could take f equal to minus g, and then this will become, this is not defined. So, some people define also, it's a force convention, it's not defined, but make a convention that degree of a zero polynomial is minus infinity. And you will see why this minus infinity and why not minus 1, why this convention is made, because of the following second formula. The second formula is very, very important. Degree of the product is less equal to degree f plus degree g. Moreover, equality holds if R is an integral domain. What is an integral domain? Integral domain is a ring which is free from zero divisors. And what is a zero divisor? That means, so That is, I will just spell it out. That is, if A and B are two elements in R, both are non-zero, then their product AB is also non-zero. Then it is called an integral domain. For example, field is always an integral domain. So for integral domain, the product of the degree of the product equal to sum of the degrees. So integral domain fields are integral domain. Field implies integral domain, but obviously not this way, because we have an example here, integers, ring of integers. This is obviously an integral domain. It is the two integers, if I take non-zero, their product is also non-zero, but it is not a field. Z is not a field. So there are many examples of integral domains which is not a field. In fact, one simple observation I will note here, if R is, so lemma, if R is an integral domain, then the polynomial ring R over R, Rx, is also an integral domain. This is very important fact. We will keep using it, and nothing special about one variable. I could repeat this argument. So, moreover, R in n variables, Rx1 to xn, is also integral domain. For any n in natural numbers, and actually not necessarily for rational numbers also, but anyway I will not need in this course. Even if you take polynomial ring in many variables, number of variables could be also uncountable, and so that will also be an integral domain, because any polynomial will involve only finitely many variables, and therefore if you have two polynomials, they will all together will involve finitely many variables, but ultimately therefore argument will come down to the polynomial ring over R in finitely many variables. So that is one. Now we are going to now little bit about this course, what we are going to central theme will be. So we are going to take a field. So K is a field, and ancient day it was taken K to be Q. This was when Babylonians didn't even take Q, they only took natural numbers. So let's say in reasonable time, that is 16th century, that people took Q. They didn't even know complex numbers correctly. So take Q, and then you take a polynomial. So we are considering the polynomial over a field. So I will keep writing a general field, but specialized to this the history. So I have this polynomial ring over K in one variable. So elements of this ring are precisely the polynomials with coefficients in K. So F is a polynomial. So F will look like A0 plus A1x plus AN xn, and this An is non-zero, and this N is therefore the degree of F. So the simplest one, obviously the constant polynomial. So that is all these AIs are, so the degree is 0. Degree 0 means precisely degree of F is 0 if and only if f is a constant polynomial. So there is nothing much to study in this. So if degree is 1, then we have f will look like a0 plus a1x. So this is called a linear polynomial. Linear, this is degree is 1. Degree f equal to 2, that will f will look like a0 plus a1x plus a2x square. Where this a1 is non-zero obviously, here a2 is non-zero. So that is also called quadratic. Qua is 2. And degree 3 cubic, degree 4 quadric or biquadratic, degree 5 quintic, degree 6 sextic, and so on. That is how the Greeks started calling them. All these words also coming from Latin. Okay, so what was the problem? The last time I saw that then we want to solve these polynomials. Solve this means what? Equate them to 0, so you get equation. So it's a polynomial equation. One should really say it's a polynomial equation. A polynomial, you cannot say, so this writing, it was allowed in the former days because the language was not so established, but as I said last time, that created also lot of confusion among people, and that led to many errors and so on. So if I have a polynomial of degree n, a0 plus a1x plus a n x power n, an is non-zero, so this n is the degree f. And then what are we doing? So we want to solve. Again, this is not so very precise. Solve the equation. Now its equation f equal to 0. So what does that mean? That means in this expression, or in this polynomial, all these a1, a0, a1, an, they are known quantities, they are given to you. And x is unknown, x is a variable, so it's unknown. So when you say solve, means find all values of x so that this equality holds. Find values of x such that f of x equal to 0. Now I cannot write capital X because capital X is a variable, so I cannot. So instead of this, then one writes, I could have used small x. We will write like this. Find all values of f, all values of small x, such that when I write capital X equal to small x, it is 0. For example, suppose I had only linear polynomial. So that means my polynomial f is a0 plus a1x. Then obviously the only small x, so that f of x is 0, that is nothing but only one value. That is, you see, last time we said, no, this means a0 plus a1 small x is 0. That means x equal to minus a0 by a1. So this was linear polynomial, so a1 is non-zero. So therefore we are allowed to divide by A1, and not only that, that means you need actually a field, because if I take a ring of integers for example and A1 is 2, then I cannot divide by 2, then the solution. So this x is called the solution of f. This x will be then out of z. So it is very, very important now when you say find all values, where are you looking for values? This information is also very, very important. So in former days, up to 16th century, people have tried to solve, of course, linear, quadratic, cubic and biquadratic, and found the formulas for these values, where it is, where solutions. So these values are called solutions of f. So let me write that also. So the values x with f of x equal to 0 are called solutions of f. And now where are we taking? So initially, formerly, when in the former days, f were taken in the field q with coefficients in q. Coefficients in q were taken because we have realized that even taking coefficients in z will not lead to solutions in general. So therefore q was the smallest possible field one could take that time, and then the values we are taking in complex numbers. Values in complex numbers. They knew sort of complex numbers, what complex numbers are, etc., or sometimes real numbers. But we need to specify where you are taking the values. And nowadays it's very, very important. Many engineering applications and many other science applications, they depend on the polynomials f, and coefficients are not in q but over a finite field f. F finite field. This double line f, the finite field. Then we are looking for solutions where? Again. So we are looking for solutions. This q may not have, I will immediately after this I will give some examples. The given polynomial, there may not be any solution in q. So again the same problem. So we have to enlarge. So that means we have to consider a bigger field. Bigger field means you are extending the operations of plus and multiplication, so that it becomes a field, and the same operation. So it is a subfield. So let us see some examples first, and then we will come back to general theorem. So examples. So first note that linear polynomial, there is nothing much. There is only one solution, and that solution is in the base field. Now that is how I will, through examples, I will also develop a language. So k field, and we have a polynomial f in kx. Okay, now solutions of solution set of fx equal to 0. Where? So first of all I will say v, that is v suffix k of f. This k. This is by definition all those elements x, small x in k, so that x is a solution of f. F of x is 0. Remember, this is a subset of k. So, if f were a linear, degree f equal to 1, then I know this precisely, V k f is precisely only one element, namely minus a0 by a1. This is only one solution, exactly one. So, where remember f we have written like this, a0 plus a1x plus an x power n is equal to degree of f. So, that means an is non-zero. Now, even for degree 2, let us see, if you take for example, if you take a polynomial like this, x square minus 2, this you think of this as a polynomial with rational coefficients. And what are the solutions? VQ of this is already you learn in the school. That means x is plus minus root 2. So, this means what is this? Then you have learned in the school that root 2 is not rational. That means there is nobody in this. So, this is empty set. This is empty set. So, again that means this polynomial does not have rational solution. So, but then where do the solutions are there? So, obviously they are all real solutions. VR of x square minus 2 are two elements, plus minus root 2. They are real solutions, and therefore they are complex solutions also. This is also same as VC of x square minus 2. They are complex solutions, right? So, therefore, it is very, very important where are we looking for solutions, and mainly many times we don't have solutions in the base field. So, we try to enlarge the field to the bigger field, and so on. So, this is what we will do it. Now, in this case solutions are this root 2. So, that means, and where did this root 2 came from? It came from this 2. If you more generally, if you take equation like this, quadratic equation like this, x square plus bx plus c, this is f, this is degree 2. So, that means the f is quadratic, and we have studied in the school that v c of f equal to what? Now, we know the formula, minus b plus minus square root of b squared minus 4c divided by 2. And these may be real or may be complex, but definitely they are complex solutions. So, one learns, and then one can also write when will VR f will be non-empty, that is if and only if this quantity here under the square root, it should be positive. So, b square minus 4c should be positive, non-negative. This is called the discriminant of f. And as you see, there is nothing special about defining discriminant of a degree 2 polynomial. I will soon define discriminant of an arbitrary polynomial. So, when the discriminant is non-negative, it has a real solution, and in fact both are real solutions. So, in fact in this case also there are two solutions in general. One may be repeated. Now, you see all kinds of questions are cropping up. For example, given a polynomial of degree n, how many solutions are there even when you enlarge the field, and how many distinct. So, all these things in next few minutes I will try to summarize. Okay, so first of all, note that all our efforts in this course will be very, very down to the earth, and mainly they will involve polynomials. and sometimes we make the abstract definitions, but ultimately we will have to come back to the concrete examples. So, if you have a polynomial f, a0 plus a1x plus an xn, this is an arbitrary polynomial of degree n, and as you have seen also, as the degree grows, the finding the solutions as well as their analysis, how many are there, and some may be repeated, like in case of the earlier example, there may be repeated when the discriminant is 0 and so on. So, all this analysis is very important for our study. So, as far as, so this is a polynomial over a field, and when we say enlarge, enlarging, so K is a field, enlarging K to a bigger field, which I will denote usually by L. What does that mean? This means you have this given field K, you look at the bigger field L, so that this K is a subfield. See, the subfield means that the same operations which are here of plus and dot, the same operations are inherited to K. So, in particular 0, which is the neutral element for 0 addition, is also the same 0 here. So, that means you can write 0 L equal to 0 K, this is 0. Similarly, 1 L equal to 1 K, this is usually denoted by 1. So, therefore, we will not have confusion, and such a thing is called a field extension. Of K. So, K is a field and field extension of K, and then we are given a polynomial f, we are looking for its solutions in this capital L, or even so the biggest possible, so that f has a zeros there, f has a solution there. Now, to do this, first of all I want to reduce the problem that we can always assume this polynomial is monic. So, what are for doing this, what are all we assume? That f is monic. That means the leading coefficient of f is 1. And how can you achieve that? I know that an is non-zero, an was the leading coefficient, and this is non-zero we know, because n is the degree, and I replace f by the new polynomial a0 by an plus a1 by an f and so on, plus an minus 1 not f x by an plus x power n. So, the coefficient has become 1 now. I have divided by a power n, simply means that I have multiplied by inverse of an to f, and this is our new polynomial. So, this is very easy because the coefficient. So, that is where I use the fact that K is a field. So, an inverse exists because it is a non-zero element, and therefore, we can always assume for our purpose. So, if x is a solution, x is a solution of f, if and only wherever that x is a solution of an inverse f. So, we can always assume for this, but remember this we can only do it when if we are coefficients, we are treating f as a polynomial over a field. If we are even doing over integers, then we cannot do this, because in integers the only elements which are invertible are plus minus 1. So, now a little bit 2-3 minutes about the problem. So now what are we looking for? We are looking for solutions, and we were looking for formulas for solutions of f. What does that mean? So the typical example is, see, linear one, we have this formula a0 by a1. It involves only the coefficients. In case of quadratic, you remember they were minus b plus minus square root of b square minus 4c divided by 2. This is a formula for the solutions of quadratic equation. This quadratic equation, x square plus bx plus c, and this was linear. So the linear also you could have done like this, a0 by a1 plus x. So you just simply send it to the other side. So these formulas involve what? They involve operations plus multiplication and division also. So these are called field operations, or minus also, plus minus. They are operations of the field, given field. You can divide in non-zero elements, you can divide, multiply, add, subtract. In addition to this, we have one more operation here, namely extracting square roots. That is where we need to enlarge Q. So these are called formulas. So one now looks for formulas for a polynomial equations, solutions of the polynomial equations where degrees are higher, degree 3, degree 4, degree 5 and so on. And as I told you yesterday, there are explicit formulas are for cubic equations, biquadratic equations, but in general there were no formula for degree 5 equation onward. And this theory evolved out of this, that how do you decide a given polynomial of degree 5 has a solution, has a formula in terms of these operations or not. And 2000 years this question was not satisfactorily answered till Galois came up with this theory that you cannot solve all the equations. This means you cannot write down formulas for solutions for all degree 5 and onwards equation, but then how do you decide the given f as a solutions which can be written in these operations or not? These are called solvable by radicals. So in this course we will develop a theory, and we will apply this theory to explicit equations, and for them there will be formulas, for the others there will not be formulas. So this created lot of good mathematics and also lot of practical problems and so on. So thank you. We will continue next time.